draw the resonance form, and that actually puts a partial positive charge on the beta hydrogen or carbon, and so that's going to be more de-shielded because it has less electron density because of that resonance form. If it was something like this, it's the opposite effect, because the resonance, we could draw that, puts a negative charge on the carbon here. And so that gives it more of a shielded effect than it would be counted.
In a tree diagram, does it matter which one splits first? Does it always have to be the highest, or can it be like...
It doesn't matter which one you do first. I like to do the first one with the largest just because it keeps everything separated for as long as possible. Once they start overlapping, it gets more confusing. But it doesn't matter.
If the VA coupling, they wrote 5
Sure. Okay, but no, if you're looking at that one, there was the 14.5 value, but that's just, it is twice the response.
Oh.
And you would see from the other peak that there was a 17 or 7.25, not a 14.25, so you know it's 7.25 for the coupling. But it's a triplet because there's two of them. Audrey?
Does that say JAB twice? I just can't read it, sorry.
Yes, because there were two neighbors. One was 2A, right? And so they're gonna, one of them's gonna split it once, and then the next one splits it a second time, but those are equal values. And then your conversion, you didn't have to, if you didn't use actual values, that's okay. But to convert your ppm values to hertz, you need to first subtract the ppm values of the two, so you have the distance between the two peaks, and then multiply by 500 megahertz because that's the strength of the instrument, hence the part written above, and that will give you the value in hertz. So if you don't have access to the computer to actually measure it, or if it's not shown on the spectrum that you're given, you have to actually go through and calculate those using that equation. So make notes on those, and then I will go through and double check all the grading and everything. I know that some of them are contingent on other things, so I'll go through and double check those. Let's practice doing this. Is it getting a little bit better?
Yeah.
Yeah, I need to do that one.
Yeah.
I have a hard time looking at, like, not the NMR, but the J coupling ones, and having a pattern in my brain of like, let's do this first and see what couples to this first. I think
Just
I get lost.
extracting out these
Yeah.
numbers.
Yeah.
So when I did that, when I was writing this out, I labeled these on the back as which ones they were. And that's, everybody else got a version of that. So when I labeled these, I have A and C and B. Okay. So between A and C, these two peaks, the common number between the two is 1.5. And so that tells me that the JAC value is 1.5. Then if we look at C and B, the common number is the 15.5, which I understand is hard to read. But that's 15.5 there, and this one's 15.5. So the JBC value is 15.5. And then between B and A, the common value is the 7.25. So write the assignment on the peak, and then match the J value, or the hertz values, and you can match them. Tell the person.
Does it matter which order they're in, like CA versus AC?
No, because they'd be equivalent. Yeah. Same question. Good. Okay. All right. So hand those in. I'll go through them. You also got back your homework and the extra credit thing you turned in a while ago. So the carbon NMR one went pretty well for the homework. some of those online things are terrible and some of them are a little bit better. A lot of them make some pretty bad assumptions. So that could vary, which one you use, and can give you better or worse answers. It also depends on how complex the structure is. If you add more complexity, your calculations tend to get more off. The extra credit is to do the fragmentation of the more complex ones. You have to do some resonance stuff, which makes it more complicated. So you gotta shuffle the electrons around by resonance, which you can move them by resonance. I was seeing one of the common problems I see in OChem where you try and draw resonance to a bond that already has 3 hydrogens to it, so you can't just move that bond over. Be careful of that. But these electrons could be moved all over the place. And as I was doing, I was realizing how complicated that one example was. Yeah, that was fun, right? Look up for something easier on your final. But when you're talking about those, you do need to know how to show the fragmentation patterns. On the final, it won't have quite that complicated of a problem.
I don't even have a thing for that.
So, any questions? All right, let's talk about cozy. Anything?
It's not. I think probably for you to do it for the stupid pre-lab, post-lab thing, because that was confusing. I really missed some organized.
So pretty much got through my brief notes about what we wanted to talk about cozy, but I have one more thing to mention, and then we'll actually go in and look at the cozy examples and how to analyze them. So one thing I wanted to mention is when you're analyzing this, you want to then assign the cross peaks with the coupled hydrogens. So if you have a peak here, what you would first do is go through and label the peaks in the NMR, A, B, C, D, and then go through and label this as A to E or A to something, and we'll go through examples of that. So that's how you want to analyze a cozy. This was the one I had on the handout, but it wasn't very good, so let me pull up the other one. I believe I gave you, no, not that one. Let me do the other one. I gave you this handout on Monday. So we're looking at 2-hexenol, not 2-hexenol acetate, that was in this number there. So this one is actually the ketone. With an alkene at the end of the chain. So again, the best thing to do is to go through and assign the peaks first. So A, B, C, D, H, E, and we'll do H, F as well. Remember that cis and trans hydrogens are going to be different. So A is easy to assign, that's going to be our methyl group here. I believe you went through and assigned these. Well, we got something, so we have D there, and then B, and C, and then H, E, and HF. C, F is going to be on this side, and D is going to be on that side. Did I switch that from what I had before? No. Same letters? Okay, good. Now, with the cozy, we're going to look at what the cross peaks are. Remember, diagonal is going to be essentially ignored, and then we're going to look at the cross peaks. We really only have to look at half of them though, because it's symmetrical. If you're looking at hydrogen versus hydrogen, you're going to get the same peak here as you do here. So we're going to look at the top half here. And in this example, we've got several cross peaks. So first thing to look at is that methyl group of the acetate does not have a cross peak except for B, and that might be a very slight coupling, but when you look at the methyl group, there's no actual splitting of the peaks, so that's a very weak interaction. But that is the closest peak to it. And methyl groups tend to give us a little bit stronger signals just because there's more hydrogens there, so they can show up a little bit more, and sometimes you see kind of a big line of peaks all the way down, probably if you have a little bit too much noise in there. The other ones, I'm going to actually open up the delta version, because when we're looking at these for cross peaks, you need either a ruler or some way to define what you're doing. Now when you open up this in delta, they still have a system. Dump me out a bit. Let's see how far we can get. The y and the x-axis are going to be kind of at low resolution with your first cozy. That's actually just telling you what it saw in the experiment, but it doesn't have very high resolution. But typically you take a proton, NMR, and a carbon separately, so you're going to have much higher resolution data. And it's easier to bring those in here so that you can correlate the peaks and see the actual splitting. So I did that. And if you're not sure how to do that, the Joel website does a tutorial on that. And if you're not in the lab, I can send you that link. Also may need to look at the level tool. So I'm going to add a little bit more signal here so we can look at it. And the level tool. And then the cursor is the one I was going for. The cursor, if I click on a peak, it's going to give me crosshairs, which is going to show me what it's corresponding to in the x-axis and the y-axis. So when I clicked on that, I now see that this peak, where I put the cursor, is corresponding to a coupling between our proton, what did we label that as again? C?
C and D.
That one's E.
This one's D. Okay. This one's D, this other one is C. Okay.
Yes.
So this one's C, C, and then we had F and E and B and A. And so we see the coupling between D and C. Now we probably could have measured the coupling constants, or we could have, and we would have known that those were coupling based on them having the same coupling constants, but the cozy is actually an easier way to tell when two things are coupling. So if you have a cozy, it's nice to confirm your coupling constant assignments. We also see that B, or C here, is coupling with the F and E. So I'm going to say this peak is our CD peak. We're seeing the coupling between those two protons. We also see C and F and C and E.
Mm.
I want you to save it. And I just want to put that. There we go. Storing there. There we go. Except it's not kind of like saying.
I asked myself that why.
So we can see that same coupling between C and F then C and E as we drag that along. And we see coupling between C and B. And so C is rather a promiscuous peak coupling from all the other ones. We have and C, D. So let's close that again.
And I died.
Alright, focus.
It was great.
We also see here that if we go down to this next peak, our D peak is coupling with F and E. So there's a coupling here, and there's a coupling here. Those are sort of overlapping, but if it was only coupling to one of them, you would see, maybe not see this side of the peak. So you kind of want to move that around and see that they're lining up really well. The last coupling that we have in here is actually a little bit more tricky to see. When you have two peaks that are really close together, and they are coupling one another, they are very close to the diagonal, but not quite on the diagonal. So if we look at this set of peaks right here, I'm going to zoom in on these. You'll see we've got our two peaks for F and E, and we do have the diagonal peak here and there, but we've got these side peaks. And if you get high enough resolution, you'll see those side peaks so that you can actually see the coupling between E and F. So these correspond to a coupling between proton E and F. On either side, you could say it's that one, or this one will correspond to the same coupling between E and F. So those at the diagonal you have to be careful with if you have peaks that are really close together. And eating some calories. Sorry. It was a good look.
So we shouldn't ignore this then?
Not be, you've just got to be careful. If there are peaks that are close together, then you got to look real closely at the diagonal. And sometimes this is just going to look kind of blobby, and you may not be able to distinguish that. That's when you may want to go back to the coupling constants and determining how strong that coupling is. If I get too much signal in here, or not enough signal, so if I take away some of this, we actually do see that. It's pretty strong coupling, so you see that. But if it's a weak coupling, you may not see it in the cozy. And if you get too much signal, then it just looks like a big old blob. You have to be careful with that too.
I'm sorry, so are you saying within the diagonal there are cross peaks?
They're just off to the side of the cross peak in this case. Or, sorry, no, let me take that back. The cross peaks are when it's exactly lining up with itself on the other axis. So here, this peak is exactly lining up with this peak on the other axis. So that's the cross peak that we're ignoring. But then we want to see the cross peak between these two.
But there's no peak there.
Well, but it's lining up, if you look here, that's that peak, coupling with that peak.
Okay.
Because it's split into a doublet, it actually, you see the doublets in the signal here, if you have a really good signal.
So what exactly are we getting from this? Because we've labeled 2, 3, and 4 bond couplings, right?
Did we get to 4 bond couplings?
Like with, I think.
Oh yeah, with the long range. With an alkene, you are going to see that kind of long range coupling. With a normal alkane chain, you may not see that kind of long range coupling. But it helps us to identify all the coupling. The peaks that are not coupling each other, let's look for those. So this peak here, this B peak, So you want to look for absence of peaks and presence of peaks. It can help you, all of this is more information to help you assign the different peaks in your signal. So you can do calculations to get an approximate chemical shift, then you look at what's coupling together to see which ones are neighbors. So you have to take all of this information from the different pieces to get a full interpretation of the spectrum if it's not a simple assignment. Rebecca and I were looking at one today. There's all around the naphthalene ring and 8 aromatic peaks, and we're trying to decide which one's which, and they're all pretty similar. So you have to kind of take all those pieces together. Let's look at the HMBC. Probably what I had posted for today, we'll do that example on Friday. It's just more of or HMQC.
I was gonna say, what the heck?
Yeah, too many abbreviations. Yeah.
I knew I was confused, but come on.
They give you this similar information. It's just multiple bonds, or single bonds. So HMQC is our other example. Let's close that out before it dumps me out completely. If you did the print off from 2 days ago or for today, you would have the spectrum. What are we looking at in HMQC? Hydrogen versus carbon. Your book talks about het core, which is the same thing, except for this is a more sensitive technique that you actually get better data from. And so we'll just refer to it as HMQC, but the analysis is going to be in the same way you would do a het core as well. So we're looking at hydrogen 1 on the x-axis versus carbon 13 in the y-axis.
Is it more sensitive than Hector?
Then het core, yes. Hector. So this stands for hetero, nuclear, multiple, quantum correlation. And I may slip up and say HMSC, which stands for a single correlation. Again, they're all giving us very similar information. It's looking at the coupling between a hydrogen and a carbon. And there's a lot of variations. You can get a lot more information. We're looking at a one-bond coupling here. So this tells you which hydrogen is directly attached to which carbon. Some of these will actually, you could do a 2-bond carbon, so you can see which hydrogen is 2 bonds away from a carbon. And if you take a HMQC and an HMBC, which is the one that does the 2-bond coupling, you can start piecing together more complex structures. And sometimes you have to do that for more complicated things like this. And so when we talked about COSY, we talked about, so this is what it's plotting. Is the hydrogen 1 axis versus the C13 axis. This info that we're going to get out of this is the hydrogen connected to the carbon. Hydrogen, carbon connectivity. Again, this can help you then assign your carbons in your spectrum, which can be complicated otherwise. In the analysis, all the peaks are important. if you look at the example here, we don't have a diagonal because you're plotting two different things against each other. So we don't have that cross of the exact same hydrogen coupling with its sulfur. We just see the peaks that tell us which carbon is attached to which hydrogen. So then when you label it, you can just label the letter or number that you correspond to each one. So if you label the structure with a letter, and the cross peak with the same letter. So you draw out your molecule and we give it a letter for a carbon or hydrogen, like we've been doing, and then you can label the cross peak as, well, we know this hydrogen corresponds to that letter or number. You could use numbers too. And then you now know that this carbon also corresponds to that.
So what's the importance of the cross peak?
In this peak, this one, it's telling you, that cross peak of the IMPO is telling you which hydrogen is attached to which carbon.
But if it was the hydrogen and hydrogen.
The cross peak, then, it doesn't tell you anything in the COSY. The cross peak of, the cross peak of a peak with itself doesn't tell you anything. You know that that's the same peak. It's the ones off the diagonal in the COSY. In the HMQC, we look at all of them. So here's a HMQC of, I believe this is sucrose. And you can see that one of those sugars has a lot of hydrogens in the same region and a lot of carbons in the same region. But when you plot them versus each other, it kind of spreads everything out. You take something from one direction and you spread it out into two dimensions, and you can then assign peaks more readily than you can otherwise. And we've got your cross peak here. So this is the hydrogen of the anomeric carbon, and you can see that the hydrogen 1 corresponds to the carbon here. Which carbons are not going to show up here? If they don't have a hydrogen connected to them, if they're quaternary, they're not going to show up.
So is it unique? So like there's only one carbon that goes with every hydrogen signal?
Not necessarily. I believe there'd be an example in here where that's not the case. So 6.
Yeah, the blue one.
Well, 6 here has 2 hydrogens attached to it, and we should see a cross peak. I'm not seeing them here. If they're diastereotopic and the 2 hydrogens are showing up differently, then they're going to show up with the same cross peak of the carbon. And that can tell you which 2 are attached to the same carbon as well. Alkenes or diastereotopic protons are going to give you that. Otherwise, unless there's 2 overlapping carbons in the carbon NMR, they shouldn't overlap like that. So 2' is not showing up in their carbon, probably because they didn't do the high res like we're going to do. But if you have 2' on here, it's probably showing up somewhere in this region. It's not going to have a cross peak. So HMQC can give you similar information that you would see in a depth. So it tells you which ones are quaternary. It can also then connect you between your proton and your carbon. And if you look at the integration of your proton, you can tell whether it's a CH2, a CH, or a CH3. And so between depth and HMQC, you should be able to assign every single carbon in a given molecule. One of these cross peaks here, one way you see that separation of the peaks, see there's 2 peaks here, 3 and 5, but when you separate it out into the 2 dimensions, you actually see the separation of those 2. Some hydrogens may show up as not having a signal in the carbon or the HMQC. Which ones would those be? Alcohol or a amide or anything not connected to a carbon. So that can give you that information as well. any different element that would be NMR active, so nitrogen, if you have the right isotope, or oxygen, if you have the right isotope, you can do that. They do that a lot more in biochemistry, where they're looking at things with lots of nitrogens or oxygens. And so as long as it's NMR active, you can do this. It's going to have different setup parameters. So this one's looking specifically at the ranges of a one bond coupling between a hydrogen and a carbon, which typically range somewhere between 50 and 200 hertz. So you'd have to know the value of the phosphorus and the carbon bond and program it all, but you can do 2D with all of those. And there's lots of different variations of 2D NMR, and they have all sorts of crazy acronyms to go through. So on Friday, we'll go through one compound completely in the analysis of proton, carbon, depth, and COSY, and HMQ.